welcome to my talk about XCLASS. It's just a brief introduction to this package. First of all, there is a new website for this preliminary version of XCLASS called XCLASS pip. So it's preliminary because it's really new, because you can now install XCLASS as a normal Python package. But it's a more complex package than usual because we have portrait routines, OpenMPI, external libraries, and the installation procedure there are some problems. I hope that we can fix them in the near future, but on the website there is my email address, so if you have problems, questions, suggestions, whatever, on the website you can find descriptions for all of the XCLASS functions. You can download tutorials, which are more or less zip files, which can now, if you decompress them, you can execute them on your local machines and play around with the different XCLASS functions. So, first of all, where can you can find help on the new XCLASS website. You can find there are the tutorials. When you download the zip file from XCLASS, the zip file contains a subdirectory called examples, where you can find example calls of the different XCLASS functions. We can see how to use the different functions and find more details described. So first of all, the question is, why should you use XCLASS? Well, the answer is this one. These are molecular lines in Sagittarius B2, and this is not noise. These are all molecular lines. And in order to describe them and to derive the physical parameters of them, you can use XCLASS, among many other things. So the most important, in addition to some other functions, the most important functions from XCLASS are the myXCLASS function itself. It's just a function to create synthetic spectra. They have the myXCLASS fit function to fit single spectra. You have the mapFit function to fit entire data cubes, not one data cube, but you can fit as many as you like. And there is the line ID function, which identifies species in a given spectra and returns a quantitative description of each of this molecule, of this identified molecule. So we start, first of all, with the core of XCLASS, the myXCLASS function. So the myXCLASS function uses the detection equation in one dimension. And the contribution of a certain molecule is described by a certain number of components. These components can be interpreted as a core or an envelope or an outflow or whatever. In contrast to other packages, XCLASS takes always all transitions into account, which are contained within the observed frequency ranges. The molecular parameters which are required to describe to create the synthetic spectra are taken from an embedded SQLite database, which contains entries from CDMS and JPL. And in addition to the standard CDMS, this database here for XCLASS contains the description of partition functions for more than 1,000 molecules for 110 temperatures, and not only 9 in the old CDMS, between 1 and 1,000 Kelvin. So extrapolation, especially for the low temperature regime, is no longer needed. Each component is described by at least these 5 parameters. So the source size, the temperature, column density, line width, and velocity offset. And the task is to determine these components. The XCLASS provides 2 different source descriptions. So here is the classical source description. So we start with XCLASS describes a stack of components. And on the one end of the component, close to the microwave background, we have the continuum. And then in front of this continuum, we have the core components. For example, you can interpret them as different components describing different molecules within a hot core, for example. And in front of this this core layer, you have the foreground components, describing envelopes and so on. And all the input, all the parameters for each component are described in an ASCII file here called molefit file, where you indicate the molecule which you would like to model with the name of the molecule, and the number of components. So here you have H2S with 3 components, and each row describes 1 component. So first component with 150 Kelvin, the second component with 68, and so on. You can use as many components as you like. You can describe as many molecules as you like. I have to mention that there is a problem with our interface to the database, because as you can see here, you have to define the name of the molecule to select a certain molecule. Sometimes a molecule has different names, and there are problems with the naming we have to figure out. But I think there's this database query function where you can get a list of all molecule names which are included in the database. In order to reduce the number of parameters, so we have at least 5 parameters for each molecule, you can use a so-called isoratio file. So the isoratio file can be used to reduce the number of parameters, because in the isoratio file, you assume that the isotopolog of the isomaster molecule has the same temperature, the same source size, the same velocity, and so on, except that only the column density of the isotopolog is scaled by a certain isoratio. For example, in this example here, the column density of 33 SO2 is 1/75 times the column density of the isomaster molecule SO2. In addition, you can define global isoratios as well. So, for example, if you have a couple of molecules, all of them containing 13C, then you can define a global isoratio for 13C, and this global isoratio is used for all of the other isotopologs. In addition, in general, you should always use spectra with continuum, and in order to describe the continuum in a more phenological way, you can use this power law to describe the continuum. And yeah, in addition to the classical source description, we have just this core layer and the foreground layer. XCLASS offers the possibility to use a more advanced source description. First of all, you can use a distance parameter. So instead of this core and foreground formalism, you can say, okay, you can locate each component at a certain distance. The absolute value of the distance doesn't matter. It's just the order of distances is important. So a distance of a high distance means this component is close to the microwave background, and a short distance means that it's close to the observer. So in this case here, for example, you have 2 components which are located in the same layer perpendicular to the line of sight. In addition to that, you can also describe components with center which are with a center which is not identical to the center of the beam. So you can place some offset or so. And this subbeam description is used whenever a component with a smaller source size is used in which is located in front of a larger source size. So, for example, you have a hot core, and in front of this hot core, you have a small H2 region. So then you have to use this subbeam description. But the subbeam description is computationally expensive, so it should be avoided if possible. Because for the subbeam description, XCLASS has to perform a 2D Fourier transformation for each frequency channel. And if you have 100,000 frequency channels, then it takes a while. In addition to molecules, XCLASS is able to describe recombination lines. So in this version, only recombination lines in LTE. Recombination lines can be described for a couple of atoms, and for each atom, XCLASS takes all transitions of the recombination line up to the theta transition, delta n equal 8. Yeah, there are there are observations with this high-ordered recombination lines. So this means that if there are, let's say, 3 recombination lines included in your observation, XCLASS try to model all of them simultaneously. In order to use or to model a recombination line in the MOLFIT file, you have to use the name starting with RRL and then followed by the abbreviation for the atom, and the column describing the rotation temperature describes now the electronic temperature, and the column describing the column density now describes the emission measure. Everything stays the same. And in addition to that, you can also describe dust. So there are different ways to describe dust. This is just one possibility. So here, in order to describe the dust continuum, you just use the phrase cont dust as your molecule name. And then the temperature is now the dust temperature, the column density is now the hydrogen column density, and the other parameters are now the kappa, the spectral index. So this offers the possibility to describe different amounts of dust for different layers. For example, if you have a hot core with a high amount of dust, and in front of this hot core, they have an envelope with another with a lower amount of dust, but which is not neglectable. So this now we can describe for each layer the dust contribution. So now the final question is how to determine the parameters. So the parameters for the different components. The first possibility number 1 is to combine the MyXClass function with a chemical code. For example, Shaptarzi is a chemical code which was developed here in Cologne. So for this code, you have to assume some density and temperature profile, and then you have your reaction rates, and then from the reaction rates you get the temperature and the density structure, and then this can be used as input for the MyXClass function. Or possibility number 2a, you can use the MyXClass fit function. So the MyXClass fit function can be used to fit single spectra. That means single spectra, not only one, you can use as many spectra as you like. For example, if you have an observation, a wideband observation, where each band has its own data file, and then you can combine the different data files to have one big spectrum. Here, for example, the MyXClass fit function was used to describe the molecular lines in the star-forming region G327, where we identify the vibrational excited levels of ethyl cyanide. And for this MyXClass fit function, extended MolFit file is required. So for each column, 3 additional columns are required describing the lower and the upper limit for the corresponding parameter, and a column called fit flag, where you can switch on or switch off if this parameter is optimized or not. Of course, you have to make sure that your initial value, in this case, for example, here, this 80.47 arcsecond, is within the limits on the left side. And then one needs, XCLASS requires settings how to import your observational data, and this is done by your observation XML file. So on this observation XML file, you can define how many files you have, and you can define the path and the name of the files. You can define different frequency ranges if you would like only to fit single transitions or whatever, or to exclude some artifacts or whatever. For each frequency range, you can define the continuum, you can define some dust parameters. For each observational data file, you can define it's an interferometric or a single dish observation. You can define the size of the telescope or the size of the beam, depending on what you have. You can define the source velocity and so on. And for the optimization, so XCLASS tries to fit the given parameters to the observational data. And in order to do so, XCLASS requires optimization algorithms. And XCLASS provides 2 different optimization packages. First of all, the old MAGIX package, which is MPI parallelized, which is very useful to describe single spectra, to describe line-rich spectra with many lines, with many parameters. And in addition to that, we now have the SkyPy package providing different optimization packages from the SkyPy package. Some of them are parallelized, some of them not. In addition to that, both packages offers the possibility to estimate the errors of the model parameters using the MCMC package or the UltraNest package. But the UltraNest package is experimental. It's included, but in my experience, the MCMC results are much more reliable. One result of the MC package is the so-called corner plot on the right, which you can see on the right side. So on top of each column, you see the probability distribution for each parameter and the corresponding error limits, or the trusted regions. And in the other rows, you can see the 2D projection of the parameters. And XCLASS offers the possibility to combine different optimization algorithms. For example, you start with a global optimization, like the genetic algorithm, and then use the result of the genetic algorithm as input for the Liebenberg-Marquardt algorithm. And then after that, you apply the MCMC package. So in general, you have two kinds of optimization algorithms. First of all, you have the so-called global optimization algorithm, which just requires the limits of a certain parameter, for example, for the temperature and so on. And in contrast to that, you have the local optimization packages like the Liebenberg-Marquardt or the TRF algorithm, which requires some initial guesses for the values. So combining the global optimization algorithm, the genetic algorithm, and the local optimization algorithm, the Liebenberg-Marquardt or TRF, you can benefit. You can take the best of both worlds. Possibility number 2b is the MyXClass mapfit function. So the mapfit function can be used to describe entire data cubes. Not only one, you can describe as many as you like. You can select a region, you can select single pixels, whatever you like. The idea of the mapfit function is that you provide a molefit file, which is used to fit each pixel spectra. And at the end of the at the end of the mapfit function, the end fitting procedure, sorry, you get temperature maps. So for example, we start with methanol with one component, and at the end you got parameter maps for the excitation temperatures. So that means that each pixel within this parameter map describes the optimized parameter value for the corresponding pixel. And in the end, you get temperature maps for each component and each molecule. So this offers the possibility to describe complex spectra, like the Sagittarius B2, and to retrieve the temperature, velocity, and density structure of each molecule, because XCLASS takes all transitions into account, and it's quite robust. But sometimes you realize that there are some kinks in the temperature map or some weird values or so. Therefore, XCLASS, the mapfit functions offers the possibility to use an iterative procedure. So first, for example, here, this is the temperature map of CH3OCHO after the first iteration. You can see it here on the upper left part, there are some weird temperatures with a very high range. And the idea is now that XCLASS uses the result of the parameter maps from the first iteration, applies some smoothing algorithm, and then use this smooth parameter maps as initial values for the second iteration. So this means that the result of the first iteration is smooth, and then for each pixel in the second iteration, the smooth temperature value for each pixel is used as initial guess for a second fitting iteration. So this helps to get a smoother temperature distribution and so on. As you can see here, now it's a lot of this wheel is removed. Maybe one has to use a third iteration, whatever. The third possibility is to use the XCLASS GUI. So the GUI is just to where you can interactively play around with values. So first, for example, you have to select the fitting algorithm. You can select the continuum, and then you can see for each molecule, you can see these transition plots. So you can order the different transitions by lower energy or by frequency or whatever. And then you can see in blue is the data, and in red is the synthetic spectra. And then in the lower part, you can play around with the temperature. You can add, you can switch off or switch on isoratios and play around with isoratios and add more components or set components as active or deactive and so on. And in the last plot, this is done for each molecule. And in the last plot, and in the third tab, you can get combined spectra where you take all the previously optimized molecules into account, and then you can also fit this transition as well. And then you have another possibility to determine the parameters. Possibility number 4 is the so-called, aforementioned line identification function. The idea of the line identification function is that first of all, XCLASS takes all molecules into account which have at least one transition within the given frequency range. So all molecules which are contained in the database. But of course, you can restrict them. You can say you only would like to fit a few molecules, methanol or the well-known SO2 or whatever. And then you have to provide a so-called default MOLFIT file. So this MOLFIT file actually describes how many components are used and the corresponding frequency, the corresponding parameter ranges for each component and each parameter. And then XCLASS performs so-called single molecule fits. So it takes the default MOLFIT file, replaces the name of the first molecule by the current molecule, and then it tries to fit the contribution of this molecule to the observational data. And then it analyzes the result of the single molecule fit by looking at each transition, and if a certain transition is overestimated, it computes a so-called fraction of overestimated lines, and if this fraction is above a user-given threshold, then this molecule is excluded. Or if it's below the threshold, this molecule is added to a final overall MOLFIT file. So this final MOLFIT file is necessary to take line blending effects or whatever into account. If you have no line blending, of course, then it's not so important, but if you have highly line-crowded sources like Sagittarius, then this is extremely important. You can find tutorials for applying the error estimation. You can find tutorials for the mapfit function and for the line ID on the web. And yeah, if you have questions, suggestions, and so on, please contact me.